So we need an antiderivative for this monstrosity, right? We want to make it simpler so that when we try to take the antiderivative, it turns out to be something that's much easier to try to imagine. Like using that power rule in reverse is key. If you have something that's t to the third and you want to evaluate the antiderivative, then you know it's got to be t to the fourth, and then there's going to be a coefficient out front because the power rule of differentiation means the power comes down and multiplies. Right now you can't directly apply the power rule because there's a square root, there's a t squared, there's a t. Too complicated for that. So we want to make a substitution to make it easier. So we could try some guesses for substitutions. Let's guess that maybe a substitution of the entire inside of that square root would help us out. U equals 11 plus t squared. Then the derivative of u with respect to t is 2t. You need to be able to take care of all the t's you see. They all need to be changed to this variable u, or else you don't have a substitution. So right now I don't definitely have it. I have this is all u, but then this is almost the same as du. I can almost make a replacement there. What I need to do is use a 1/2 power on the outside, not 1/2 power, 1/2 coefficient on the outside and a 2 inside, because the 1/2 times 2 would bring us back to where we started. And now I have du. Now I'm ready to make my substitution. So as a du in the numerator and then the square root of u in the denominator. Now I have everything in terms of a new variable, in terms of u. And look, I dropped the limits of integration because often when you change variables from t to u, then that should change the limits of integration because you're dealing with a totally new variable. It's easiest to just put those limits of integration after you've found the antiderivative. Now, this is the same thing as 1 over the square root of u du, so that's the same thing as u to the negative 1/2 power, right? Because the square root is a 1/2 power and it's in the denominator. So I can use the power rule now that I've substituted nicely. If you were to take a derivative of something and you want it to be negative 1/2, then you could imagine that the original function has to be 1/2. Now if you take a derivative of this with respect to u, you're going to get 1/2 u to the negative 1/2, which is what we want, the negative 1/2. But we have to have that 1/2 on the inside. Just thinking about it. My mind's kind of blank about what we can do with that. Let's just leave that 1/2 on the outside. I can't really seem to think of whether we could move that in the inside one. Yeah, the antiderivative would be u to the 1/2. Oh, okay, but we need a 2 here. Because if we didn't have that 2, this isn't the actual antiderivative of u to the negative 1/2 power. Because when you take a derivative of this with respect to u, the 1/2 comes down, and then we take 1/2 and subtract it by 1 to make negative 1/2. So it's close, but we need to have that 2 out front to cancel out the 1/2 that's going to come down. So we found the antiderivative. Now we don't need the variable u anymore. Let's plug our substitution back in there. The 11 plus 2 plus t squared in for u. Oh, t squared, right? 11 plus t squared. That's the 1/2 power. In other words, the square root. And then our limits of integration were 0 to 5. We can put those back in because now we're talking about t. And 1/2 times 2, we can cancel that out, which is kind of what I was thinking about up there, but I couldn't exactly picture what it was supposed to look like. So now we'll plug in 5 and see what happens. The 2's canceled out. So we got, it's a 1/2 power means a square root. So you got 11 plus 25. That's what happens when you plug in 5. That's the upper limit. And then the lower limit was 0. So we got to find out what happens when you plug in 0. 11 plus 0 squared. So it looks like our final answer is 6 minus the square root of 11.